Okay, geometry, pause and give this a try. And come back. Okay, so after across the x-axis, we have opposite y's. Across the y-axis, opposite x's. And across the parent linear equation, we have the inverse locations, right? 3, 4 became 4, 3. You're identifying and drawing translation. A translation is a transformation where all the points of a figure are moved the same distance in the same, you got it, direction. And so as we saw with yesterday's reflections, a translation is an isometry, right? So the translated figure is congruent to the pre-image. Is A translation? Please pause and then come back and check. And you're right, it's not. Is B? Yep, good job. How about A here? Is this a translation? Yep. And B? Nope. Good. A translation is a transformation along a vector such that each segment joining a point and its image has the same length as the vector and is parallel to the vector. So this is a translation vector, and so this is point A and its image, which has the same length and direction as the vector. So if you were asked to draw translations, you can use your vector knowledge to do so. We're asked to draw a translation along vector V. So vector V is here, right? So we could draw parallel lines through all other vertices, parallel to the vector, right? And then we would need to measure this vector's length, and then from each vertex, follow that parallel line, the same distance, and draw a point when we've reached that same distance on that parallel line. So we would have kind of a little parallel vector, right? And that's exactly what they've done here. So they've drawn a point out on each of these parallel lines, the same distance as you find in this vector along each of these from the vertex, right? And then we draw or connect the points of the images, right? And you have, boom, A translated, in this case, quadrilateral. So here's another opportunity. If we were going to translate this vector now in the opposite direction, once again, parallel lines from to the vector from each vertex, right? Measure the vector and plot a point that distance from each vertex along that parallel line, and then connect those points. So try it. You can try it right here on this, and it should look like, there's our points, each the same distance from the vertex, and there you have a translated, in this case it looks like a trapezoid, huh? Okay, recall that a vector in the coordinate plane can be written with this notation. We travel a certain distance in the horizontal direction and a certain distance in the vertical direction, right? We go from an initial to a terminal point. So a horizontal translation is going to be some change in the x value, right? So we have a point xy. It becomes point x plus a y, right? And that a could be positive or negative. In this case, the a was positive. It became greater, right? We could add a negative and travel that way to the left. A vertical translation along a vector would be adding to the y value, right? So here we have xy becoming x, y plus b. And then a general translation could be stated as we go from a point xy to a point where there might be a change of x, x plus a, and a change of y, y plus b. So we go add and we add in both the horizontal and the vertical directions. And of course, remember, we could go negative as well. Okay, so drawing translations in the coordinate plane, we want to translate the triangle with these vertices along this vector, which means that the image of the original will have a change of 3 in the horizontal, right? And a change of -1 in the vertical. So that's how we could write it in the form of a rule, right? So go ahead and complete this, and then can you diagram the original and the image. Come back. All right, so when we add 3 here, we get 0. When we take away 1, we get -2, right? And this one became 8, 4. And this one became 1, -3. So if you graphed those, it would look something like this. And it does look like a translation, as though it slid down and over. Okay, there is a second example in your notes, and we could do the same sort of thing. This time the vector is -3, -3, so we're changing the x values by subtracting 3 and the y values by subtracting 3. You don't need to write this down, just take a look at what happens. If we subtract 3 from each of these, what do we get? And from each of these, we would get, and subtracting 3, good. And finally, we would get 0, good. And so this is what it would look like. And once again, we have the original in blue and the translation in red. So let's try this as an application, kind of tricky, looking at the terms in this way. A sailboat has coordinates 100 degrees west and 5 degrees south. The boat sails 50 degrees due west. Then the boat sails 10 degrees due south. What is the boat's final position? What single translation vector moves it from its first position to its final? So if a sailboat has these original coordinates, 100 degrees west and 5 degrees south, we could plot that on a coordinate plane, and west would be, as we look at a compass, we would say it would be to the left, right? And south would be negative down, right? So we could start at 0, 0 on a coordinate plane, and the beginning coordinates were -100, right? And each of these units represents 25, right? So -100 and -5. In the vertical direction, each unit represents 5, 25 in the horizontal. So the boat's second position was the boat sailed 50 degrees west and 10 degrees south, right? So we would travel 50 degrees west, which would be -50, right? And south 10 degrees, which is now at -15, right? So we are using what we just learned by subtracting 50 in the x direction and then 10 in the y direction. So we get the final coordinate of -150, -15. Here it is. So what vector would move the boat directly to that position? And that would just be from the starting position, moving -50 in the x and -10 in the y. So that's pretty easy to find this final vector. It was just from the starting position, what was the movement in the x and the y. Good. I'm kind of noticing that they didn't use the right notation here. Shouldn't they use our vector notation, right? So you might want to change that in your notes. In this last example, suppose a drummer starts at the center of a field and marches along the vectors that you see here. What would the drummer's final position be? Well, if the drummer's starting at the center of the field, we would consider the starting point to be 0, 0. So we could lay a coordinate plane right there, okay? And then the drummer is moving this far in the horizontal direction, and it looks like moving from 8 to, -8, right, to +8. So it looks like a move of 16, right? And then this far in the negative direction, and each of these is representing 8 units, so -24. So if this was 0, 0, the drummer has traveled 16, right, and -24. So there you have it, the drummer's coordinates. Start at 0, 0, and then they would move that far. Now, in this original graph, it's like we're shifting the coordinate plane, huh? It's almost like we're sliding the plane. Or we could consider that we're sliding the drummer to 0, 0. Interesting, huh? Okay, pause, try the quiz, come back. Does this appear to be a translation? Yes. And hopefully you have something that looks like this, right? And if you were going to translate the figure with these vertices along this vector, there's the proper vector notation, then where would this point be? Take away 2, add 0, so 6, 2, and so on. You should have these values. Pause and come back with the correct values for the image of these points. And there you go. Good job. Please pause and come back and we'll talk about it once you've tried this. So if the rook is on the chessboard at 3-4 and is moved up 2, that would be the y direction, right? It would now be at 6, and then 3 spaces to the left would now take 3 away, right? So 0. So we would have the coordinates 0, 6. So what vector would move? Well, what did we just do in the x direction? And what did we just do in the y direction? Wasn't it moved up 2? So there's your vector that would get you to this position. And there you go.